All right. So here we are. We're going to get into the real meat of the matter of enzymes. Now, we've talked about enzymes in a couple of different capacities so far, but here we're going to get to the some of the quantitative parts of the study of enzymes, and we'll get into some pretty cool stuff. With that, there we go. All right. So what we're going to be pretty much focusing on here is binding patterns, because we've already talked about transition state, free energy changes, and enzyme classes. Now, let's go ahead and imagine that if you remember, we talked about this enzyme previously, lysozyme. Lysozyme was an enzyme that's capable of binding the peptidoglycan layer of cell walls. And so what it does is it breaks this polysaccharide. Now, this black molecule in the middle, that's our substrate, and then the rest of it is our enzyme. But there's some places to kind of highlight. In blue is our substrate binding site. In red are the enzyme or the amino acids that make up our active site. Now, in an enzymatic reaction, it's pretty reasonable to say that you might have substrate A and substrate B. So there are some reactions, some enzymes that have multiple substrates. Now, when that happens and these two substrates bind, you have what we'll refer to as the ES complex. Now, when that ES complex basically forms, your enzyme changes, and that's going to result in a reaction between substrates A and B. Your ES complex, denoted by this little star as well, is where that reaction is taking place. Now, the substrates are going to affect enzymes on binding. Now, your substrate A has become product C, and substrate B has become product D. And just so you can kind of keep track of all of this, what we have is simply a part of A has moved to B. So it's always exciting to think about there's this very elaborate and complicated way of studying a change where what a substrate is going to undergo, but it's actually not that complex and not that complicated. It can be very complex, as we see when we look at the specific mechanisms, but it also can be kind of simple and straightforward. Okay, so this is going to be our EP complex. And this is where our enzyme and our product are still bound to one another. Now, our product C is going to be released, and then our product D is also going to be released. Our enzyme has been freed, and it's capable of binding more substrates. So this reaction can begin all over again. So we have our enzyme plus our product. Now, all of this is ultimately reversible. We kind of talked about the reversibility of a reaction previously, where we talked about, yes, an enzyme is going to lower the activation energy for a forward reaction. It's also going to lower the activation energy for a reverse reaction. Now, the feasibility of this reaction, yeah, it might not happen, but 1 in a billion going in reverse, but it's still possible to take place. So here are the basic steps in catalysis. Now, there are multiple types of reactions. This is independent of multiple types of enzymes. This is multiple types of reactions with respect to kind of a reaction pattern. Now, there are single substrate, single product reactions. Simple as can be. A is converted into B. Single substrate, multiple products. A is converted into B and C. There are multiple substrates, single products, so two things come together to make one. Multiple substrates, multiple products, and well, basically A is converted to C, B is converted to D. Now, that is not, this is just the pattern. This is just the model. So don't think about this as, oh, well, the major parts of A remain as C. No, these are just kind of identifiers. So don't stress about that. Now, this is where we're going to kind of begin dissecting and looking into a couple of these different patterns. So types of reactions, we're going to look at ordered, random, and a ping pong model. Now, before we get into that, there's an equation that y'all need to be familiar with, and that is the Michaelis-Menten equation. The Michaelis-Menten equation is determined under the circumstances where the enzyme is saturated and the velocity of the reaction is maximal. So the enzyme is saturated with the substrate. So basically, whatever amount of its substrate it needs, you give it 10x as much. And this is something that you experimentally determined. You evaluate it. You start out with, a low concentration. And you might not know what that concentration is. So you start out with concentration X, and then you increase it, you increase it, you increase it. And you basically increase it until the velocity that the reaction is being catalyzed at no longer increases. So one thing that you can say is that when substrate concentration is very high, all enzyme substrate or substrate binding sites are going to be occupied by the substrate. So effectively, whatever amount of substrate you have or enzyme that you have at a given time is equal to the amount of the enzyme substrate complex that you have. Now, here's a couple of things that are worth noting about this Michaelis-Menten equation and this Michaelis-Menten kinetics. You have a plot, or your enzyme data is plotted with your y-axis being your enzyme, your velocity, and then your x-axis being your substrate concentration. This is known as a Michaelis-Menten plot. Now, what I was saying a moment ago was when you're doing a reaction, when you're catalyzing a reaction, you're going to say, maybe you have no idea of the desired concentration of your substrate, but what you're going to do is you're going to say, let's just put a number. We have purified our protein and we have 5 millimolar of substrate. And so we basically give our enzyme 5 millimolar of our substrate. Okay, so that's my x-axis. And then what we do is we track this and we determine that the velocity of our reaction, I'm just going to put a number together. Let's say that it's 4 nanomolar per second. So your velocity is not so different from like a traveling velocity. It is a quantity per time interval. Now, enzymes can have vastly different velocities. Some might be 4 millimolar per second, or some might be 10 micromolar per hour. It varies. So this is effectively trial number 1. Trial number 2, what you're going to do is you're going to increase your substrate concentration. Let's go to 10 millimolar substrate concentration. And then we see the velocity go up to, let's say, 6 nanomolar per second. Okay, so effectively what we've done is we've doubled our concentration. I'm going to go ahead and draw this line that's 10, and then we got 6. Okay, so we see a trend. We see an upward trajectory. And so you basically continue doing this. And you, over time, you come up with a data set that looks a little bit like this. And what I want you to notice is that this is trial 1, this is trial 2, 3, 4, 5, 6, 7, and so on. what you see is that as your substrate concentration increases, which is what we were doing for trials 1, 2, 3, 4, 5, 6, 7, our velocity increases. But if you look on this y-axis, well, the velocity increases until it kind of plateaus. And effectively, whenever it plateaus, it's kind of toast. It's kind of toast in the sense that the only thing that you could change to speed up the reaction is to add more enzyme, in which case you would not be able to compare those trials to any of your other trials because one variable, the enzyme concentration, has changed. So, another thing that you can do, rather than increasing the substrate concentration, you can decrease it. And we'd expect to see something that looks like this. Okay, now that's an important way to visualize enzyme data. I'm going to erase some of these data or some of these markings on here because I want to bring up these very important kinetic parameters. This right here, this is known as a Vmax, a maximum velocity. So it's kind of like a top speed. It's nothing more complicated than that. No, like your enzyme catalyzed reaction is not going to go any faster. Now, that's one of your important kinetic parameters. So I'll say here, erase, 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 erase. And if you can hear heavy breathing, that's my dog, one of my dogs. So we've got Vmax, and that's one important kinetic parameter. The other important kinetic parameter is to take the value of Vmax on your y-axis and basically cut it in half and say, okay, well, here is that halfway marker. So Vmax divided by 2, okay? And then you figure out the coordinate. Let's say that this is, I'm going to give a value, let's call it 12. Doesn't really matter what it is exactly. This is just an example. That is our y value. What we want to do is see how that coordinates to my x value. So disregarding these markings. That is what is known as a Km. So my Km, another way to put it is substrate concentration. So I'm going to bracket substrate at Vmax divided by 2. Okay. So Vmax is your enzyme's top speed, and Km is the amount of substrate needed to get your enzyme to half of its top speed. Now, what I always like to do with these two values is I like to think about them in terms of values, like quantitative values. For starters, Vmax. What are the units that Vmax are going to be in? Well, they can be variable, but they're going to be in something like, let's say, micromolar per hour. So we have a concentration, typically, is what it is going to be, a concentration per time interval. So just as micromolar per hour works, so too does nanomolar per second or molar per day. That would be kind of unexpected, but nevertheless. Okay, so those are our potential um, quantities of Vmax. Now, Km, on the other hand, Km is kind of confusing because lots of people hear it as, well, Km is Vmax over 2. It's not. Km is the concentration that gets you to half of Vmax or that gets you to Vmax over 2. So if this right here is our Vmax over 2, then this right here is our Km. So Km needs to be in something that is a concentration. So nanomolar, molar, micromolar. Let's go with molar. Well, I already use that. Um, Picomolar. There we go. PM. So those are our two important kinetic parameters, and those are the possible values of those kinetic parameters. Now, let's get back to the show with the Michaelis-Menten equation. When we saturated our enzyme with our substrate, we effectively are looking at the maximum velocity of our reaction as being equal to this rate constant, K sub 2, which K sub 2 is the rate constant that takes our enzyme substrate complex to our product plus our free enzyme. The enzyme is not always saturated, so velocity at all ranges of substrate concentrations is given by the Michaelis-Menten equation. So this graph that we put together just a moment ago, well, one of the things that's kind of tricky about it is that it's not linear and it kind of plateaus out. So the curve to it, sorry, is typically going to be hyperbolic. But this equation, V sub 0, which is the label for our y-axis, is equal to Vmax times our substrate concentration divided by Km plus our substrate concentration. So with this equation, if you were to take values, if you were to be given, well, substrate concentration is blah, Vmax is blah, Km is blah. What is V sub 0? Well, this equation even accounts for this range where we've saturated our enzyme with our substrate and where our maximum velocity is not going to increase, or sorry, our velocity is not going to increase. It's basically going to stay pretty much flat because it's plateaued. So if you were to take those values and come up with a V sub 0 there, what you'd notice is that even when your Km is 100 times your substrate concentration, your V sub 0 is going to be just a little bit lower than your Vmax. Even when it's 500 times substrate concentration, your V sub 0 is just right there against your Vmax. You're not going to be over. It's not going to be. It's not going to be considerably less than. So the rate of an enzyme catalyzed reaction V is determined by the constants Km and Vmax and the concentration of the substrate. Now, another very important plot that you should be familiar with is similar to that Michaelis-Menten plot in the sense of the y-axis deals with your initial velocity and your x-axis deals with your substrate concentration. But this is known as a Lineweaver-Burke plot. This is a double reciprocal plot. So it takes the values that make up our x and y-axis for our Michaelis-Menten plot, V sub 0, substrate concentration, and simply takes the reciprocal values and gives us a plot that's a linear representation of this. Now, what's great about this plot also is that it gives us a very easy way to calculate our Vmax. It also gives us an easy way to calculate our Km. Now, being able to process and understand a Lineweaver-Burke or a double reciprocal plot is going to be very helpful for being able to understand enzyme inhibition patterns, which we'll get into in a little while. But for the time being, what I want you to do is look at these axes and look at these intercepts. The y-intercept, whatever value that is, right here. If it's 5, let's say that's 5, that is equal to 1 over Vmax. One of the things that people always have a tendency to make a mistake on is they say, oh, well, I can see the y-intercept is 5, but that's a reciprocal value, so it's 1 over 5. So then they say 1 over 5 is equal to 1 over Vmax. That's simply not the case. Instead, your y-intercept is equal to 1 over Vmax. So you would say Vmax you do the algebra, and you'd say that 1 over V max is equal to 1 over 5. Okay, next up, right there, we've got a negative x value. This is in quadrant number 2. It is on the x-axis. It is a negative value. So -5, or let's go, we'll change the number, -4. If this value is -4, that is equal to -1 over km. Again, don't make the mistake and say, oh, well, I need to look at it as an absolute value. You don't. Read the plot and say, oh, well, it's -4. So then I'm going to do the algebra. I'm going to say -4 is equal to -1 over km. These negative values, I can cancel those out. Then I can go ahead and do the algebra and come up with km is equal to 1 over 4. And you'll be in good shape if you follow that. So this is a double reciprocal plot. This plot is made by taking all of the data that one would put together for a Michaelis-Menten plot and taking the reciprocal value of them and plotting them. Now here what we have is an example. If I need to erase some of my markings, I'm going to erase everything on this slide. Here we go. So if your y-axis or your y-intercept was 0.1, your Vmax is going to be 10 because it's 0.1 is equal to 1 over Vmax. Vmax equals 10. If your x-intercept is -5, well, do the algebra and you figure out that km is equal to 0.2. Now, understanding that's very important, but here where we're going to go is we are going to be entering our discussion of our types of reactions and our multi-substrate, multi-product reactions. Specifically, we'll talk about bi-substrate reactions. The Michaelis-Menten model of enzyme kinetics was derived for single substrate reactions. Okay, so it's kind of like A yields B plus C. A yields B. That's it. So then, with that in mind, this Michaelis-Menten model for kinetics is pretty awesomely simple and straightforward. So then, how do we interpret that? How do we deal with that? How do we use that information? And well, it's all doable. The majority of enzyme reactions have multiple substrates. So it's good that we can take this Michaelis-Menten model and apply it to more complex structures, more complex systems. Bisubstrate reactions account for 60% of known enzyme reactions. So really, it's kind of funny, the Michaelis-Menten model for studying enzyme reactions was a little bit, a little bit of the less common reaction. Okay, so a bisubstrate reaction, a large proportion of bisubstrate reactions are transferase reactions or oxidation. Transferase reactions, we talked about those, you'd use ATP plus substrate and yield subs plus ADP as an example. Here what we have is trypsin, which is going to use a hydrolase, or which is a hydrolase, which is going to release this group, and it's going to break this peptide bond right there. Alcohol dehydrogenase is an oxidation reduction reaction, which uses the redox cofactors NAD plus and NADH to catalyze the reduction of an alcohol to a aldehyde. Yeah, sorry. Okay, so I've revealed that yes, this is a model that you can use, but how do we actually make this work? How do we make a bisubstrate reaction look like a unisubstrate reaction? Well, remember when we performed the kinetic analysis of a substrate by determining the rate at various substrate concentrations from When substrate concentration is super low compared to your Km, to substrate concentration is super high compared to your Km. So basically what this is saying is if your data looks a little bit like this, we accounted for substrate concentrations way down here as well as concentrations way up here. Now, to make a bisubstrate reaction perform like a unisubstrate reaction, we keep the concentration of one substrate reaction at saturation, or one substrate at saturation, while studying the other substrate. So essentially what that would mean is, let's say that well, basically what we would do is we'd say, all right, well, we're going to use substrate B at this range when the concentration is super high. And then what we're going to do is, I'm going to change colors here. We're going to use A. We're going to use it at low concentrations, and we're going to gradually increase the concentration. We're going to continue increasing the concentration until, well, our reaction doesn't do anything new. And then what we're going to do is we're going to switch. So essentially what this means is that you have two substrates for a given, or for a bisubstrate reaction. You have substrates A and you have substrate B. A has an affinity for your enzyme. B has a different affinity for your enzyme. So those are going to be, your KMs for your two different enzymes are going to be different. And remember, your KM is the amount of substrate required to get your reaction to half of Vmax. Now, I'd like to add one more thing here. Km, in addition to being the amount of substrate needed to get to Vmax over 2, Km is also a measure of affinity for a substrate. So essentially what this means is that if Km is the amount, Km is a measure of affinity also, or it's also considered to be a measure of affinity. What this means is a high Km means low affinity. Now, I'm going to clear some of this because just to speak on a little bit of an aside here, I always kind of think about it like a currency. So my name is Joel. And let's say that you hire me to mow a lawn. Okay. And I tell you, listen, if you give me $1,000, I will mow your lawn and I will be done mowing your lawn in 15 minutes. Okay. That's something where you're going to say, like, well, listen, I don't need you to mow the lawn as fast as possible. That would be your maximum velocity. I don't need that. So let's settle on something. What is a price where you'll do it half as fast as you possibly can? That's effectively your KM. So let's say that my KM, my price point is, let's go with 75 bucks. Now, if you gave me a little bit more, I'm going to do it a little bit faster. But we agreed on $75. So I'm going to mow the lawn. That's that money, that rate, that wage is enough for me to do it. Not do it as fast as I possibly can. We're not really getting into the details of like, oh, what did you do the weed eating sort of thing. But if you give me $75, I will know it half as fast as I possibly can. Okay. Now that's like I can advertise that my KM for mowing lawn is $75. Now, let's say that your friend comes along and they say, "Oh, I need you to mow my lawn." Okay. Mow lawn, same job. But then they say, "But here's the thing. Um, I only have I just got back from a vacation in Japan and I exchanged all my currency for the yen, um, which, if I remember correctly, um, I think that the symbol for the yen is very similar to US dollar, or it's kind of a similar thing. I think it's a Y. I'm not sure how many lines, so I'm going to stop right there. Um, and I could not tell you the conversion rate, so this might be kind of like a laughable sum. Um, but at any rate, you're telling me, or your friend tells me, like, listen, I need you to mow my lawn. Um, all that I have are Japanese yen. Um, and you know what? The the best I can do, let's agree on this rate, like half as fast as you possibly can. Um, I think the yen's like I think it's like thousands. So let's say I'm gonna pay you 12,000 yen mow the lawn. Now, those numbers are vastly different. But let's just imagine that the exchange rate is equal. So we're not gonna worry about that. Um, but I'm doing the same job effectively. I'm mowing both these lawns, and we can imagine that the lawns are similar enough. But one of these is arguably better and easier for me. And that would be this right here to accept US dollars. Because, if I accept 12,000 yen, oh, well, maybe I got a little bit more money. I don't know. But what do I have to do with that yen? I've got to take it to, a bank or take it to customs or something like that and exchange that for US dollars. In which case, my affinity for the Japanese yen is relatively low. My desire to do the job for the exact same amount is not really that strong because I don't want to pay. I don't want to accept that. So this is kind of like how I hope that you went with me on that journey and followed. Um, if we take an enzyme like hexokinase, hexokinase is an enzyme that takes on glucose and mannose. And the Km, I'm just going to come up with numbers here. For glucose is 4 millimolar, and mannose is 12 millimolar. Okay, so in both cases, if glucose ends up with, or sorry, if hexokinase is given 4 millimolar of glucose, it's catalyzing its reaction half of max speed, half of its max velocity. If it's given 12 millimolar of mannose, it's catalyzing the reaction at half of maximum speed. Now, effectively, what this means is that these two substrates, they're not the same. They're not the same based on structure, name, anything like that, but they're also not the same from my enzyme's perspective. This enzyme kind of has a preference to bind and utilize glucose. We don't really know why. It's probably something structurally about the enzyme, but that is signified by a lower Km. So lower Km means high affinity. A higher Km means low affinity. So this right here, I'm going to add the other part. Low Km means high affinity. Yeah, eraser. That's where we were. Okay. Now, so that brings us up to speed on Km, Vmax, and some of the nuances of Km and Vmax. Um, Now for our binding patterns. Substrate addition and product release. The order of substrate addition and product release in most enzymatic reactions follows two reaction mechanisms. There's a sequential, where all substrates must bind to an enzyme before the reaction occurs and products are released. There is ordered sequential and random sequential. There is the ping pong reaction. One or more products are released before all substrates have been added, and an alternate stable enzyme, form F, is produced in a half reaction. Now, here is what we see when we look at a sequential reaction. So for our sequential reaction, what we see is our free enzyme. Now, what I want you to do is, this is where all substrates must bind the enzyme before the reaction occurs. Look along this line right here. This is our reaction path. We start with E, we end with E, okay? Now, up here are our substrates. Subs. A is a substrate, B is a substrate, P is a product, and Q is a product. Okay, now in a sequential reaction, A is the first substrate that will bind to our enzyme. B is the second substrate that will bind to our enzyme. So in a sequential reaction, an EA complex is formed. Then an EAB complex is formed. Once that EAB complex is formed, that's when our reaction is going to take place, where we're going to generate our enzyme and product complex, and that is EPQ. Now, P will be released, leaving behind our enzyme plus the other product, Q. Then Q is going to be released, which is going to give us our enzyme. Now, there's a couple of things to bring up about this. One, our enzyme. Our enzyme was a constant. E was a constant. E never changed. What E was bound to changed, but E was always E. Okay? I bring that up because in one of our next models, we'll see it a little bit differently. Now, this is an ordered sequential reaction. A must bind before B, P is released, and then Q. In a enzyme that follows this sort of mechanism, B will never bind, and then A will bind. It will always be A binds, then B binds. Now, these letters, this E, A, B, P, Q, and so on, this is what's known as the Cleland nomenclature. Okay. Now, that's, like I said, an ordered sequential reaction. So if there's an ordered sequential, then there must be a disordered. But it's not disordered. Instead, it is a random sequential model, where a reaction shows no preferred order of substrate addition and product release. And this is, again, following our straight lines and what is written below those lines. E, 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 E. Okay. Now, our enzyme, if it follows a random sequential pattern, what you could have is one round where A binds, then B binds. You arrive at EAB. Okay. And that EAB down here, that's not significant. It could be EBA. It doesn't really matter. Because an alternative to that is where E binds to B, and then A binds to EB, giving us that EAB or EBA complex. Once that all forms, a reaction can take place and our products can be generated. Our products are going to be released either P first and then Q, or Q first and then P. And we're going to end up with our free enzyme again. Now, That those are ordered and are random sequential models. A ping pong reaction is one where one or more products are released before all substrates have been added and an alternate stable enzyme form F is produced in the half reaction. Okay, so here what we have is our enzyme. E binds to A. And then what we see is our reaction takes place with EA is formed. EA leads to FP. Whoa, whoa, whoa. Okay, E becomes F. A becomes P. Our first product is released, leaving behind this modified form of our enzyme. This modified form of our enzyme is capable of binding B, our second substrate, forming EB, which then goes on to form EQ. Q is released, our free enzyme is present. Now, here's where I think there's lots of great test questions that can come from this sort of slide, this sort of concept. One of which is the question of, given this model, what affinity, high or low really, are your answer options. What affinity does E, your free enzyme, this guy right here, have for B, our second substrate? Does it have a high affinity for that or a low affinity for that? You'd be right if you were thinking that it has a very low affinity for that. It doesn't really want to bind B. What wants to bind B? Our modified form of our enzyme, F. That modified form of our enzyme F can form FB. Okay, so it can bind B. Just as F doesn't want to bind A, E doesn't want to bind B. And that's because our modified form of our enzyme is different. Okay, now the last thing that I want to talk about are two additional kinetic parameters. One of them is kcat. This is known as the turnover number, and it's a measure of catalytic activity. When E is saturated with a substrate, the observed rate constant is the turnover number. The turnover number is the number of substrate molecules converted to product per enzyme active site per unit time, and so on. So the way that this is calculated is by taking by taking your maximum velocity and dividing it by your enzyme substrate or your enzyme concentration at a given time. Now, it gets kind of complicated because really what this is getting after is not so much enzyme, but instead active sites. So if we were to look at, let's calculate the kcat of two enzymes. So enzyme A and B. Let's say they both have a Vmax of, I'm going to give a nice round number, 10. Okay. Now, let's say that we simplified this down as much as possible, and this is 10 per 1 unit of enzyme. Okay. So on the surface, you'd look at this and say, okay, well, we've got our maximal velocity of 10 per individual enzyme. Okay, so each of these have a kcat of 10. Makes sense. Okay, well, here's where it gets complicated. Because let's say that enzyme A has 4 active sites. Okay, if enzyme B has 4 active sites, well, what we want to do is actually sub this 1 out for 4. So it'd be 10 divided by 4. And when you do 10 divided by 4, you get 2.5 as our kcat. Because what we're doing is we're looking at per enzyme per active site. So if something has 4 active sites versus 1 active site, your kcat is going to be different. Now, what's significant about this is that kcat accounts for a number of active sites. And kcat Arguably, the higher, the better. So, if you have something that has four active sites, okay, so let's A versus B. If A has one active site, oh, just happened there. It has one AS, one active site, and B has four AS. Ooh, if we compare those active sites, which one's better? Which active site is better, A or B? A, because A can do the job. It can convert 10 reactants to products in the same time that B has four active sites doing that same work. Okay, so now the last kind of combination of kind of parameters that we want to look at is a measure of catalytic efficiency. And this is where we take a calculation over Kcat and divide it by Km. Under physiological conditions, substrate concentration is generally not saturating, or substrate is typically less than your Km. Now, what we are able to do is calculate how perfect and efficient an enzyme is. Kcat over Km is an apparent second order rate constant. It measures how the enzyme performs when substrate concentration is low. The upper limit for Kcat over Km is the diffusion limit, the rate at which E and S diffuse together. In water, the rate constant for diffusion-controlled reactions is 10 to the ninth molarity per second. Now, the way that I always kind of think about this is you want to be able to, Kcat is almost like a measure of strong active site. Km is affinity for substrate. So essentially, the higher that this number, this ratio, this Kcat over Km is, the higher that value is. Basically, the stronger or greater likelihood that your enzyme will kind of suck up one of these substrates and convert it to a product. Because if you have a very, very high Km, a high Km means a low affinity. You don't want a low affinity because what that means is essentially your enzyme has to be like searching for that substrate. And then finally, when it finds it, if the Kcat is high enough, then it converts it easily to product. So what we want is a very high Kcat over Km. Or the higher the ratio is, the more efficient your enzyme is. All right. Well, that wraps up this. In our next conversation or lecture, what we're going to be getting after is we are going to be getting into how enzyme catalyzed reactions are inhibited and the different types and the patterns for those inhibition. All right, I hope this was helpful. Have a good one.